In this video, we'll be talking about the universal law of gravitation and a lot of the formulas sort of related to it, like escape velocity, energy of an orbit, energy of gravity even out to infinity. So we'll explain all these formulas and what they all mean in the corresponding parts in this video. So the first formula, of course, you need to talk about the universal law of gravitation. So the force between two objects, two large objects or two small objects, it does not matter, attracting each other is equal to the gravitational constant times their masses times the distance squared between them. And the gravitational constant, you're going to be using this so much you're likely going to memorize it, but it's 6.67 times 10 to the power of negative 11, which is quite weak, honestly. This constant decreases the force of gravity, the strength of gravity as a force. But we have the unit for gravity, which is Newton meters squared all over kilograms squared. So this is the gravitational constant. You're going to be using this a lot. Hopefully you have a formula sheet for this. If you don't, poor you. My teacher gave it. Okay. So using this formula, you can derive a bunch of other equations. So let's actually just box this in. So this formula right here is big. And you can derive other equations like the gravity or the acceleration due to gravity of a planet near its surface. So again, the gravitational constant shows up and we have the mass of the planet all over the radius of the planet squared. That's represented by big R. So the mass of the planet, in some formulas you're going to see a big M and a little m. And usually in orbit formulas you're going to see that. The big M stands for the mass of the bigger object and the little m stands for the mass of the smaller object. And let's show you those formulas. So the escape velocity has one of the big M's I'm talking about. So the escape velocity formula is 2 times the gravitational constant times the big M, or the mass of the planet that you're trying to escape, over the distance you are from the center of mass of the planet. So how about for energies? Well, the energy, or the potential energy, the total potential energy that something has, is represented by, or gravitational potential energy more specifically, negative G m1 m2 all over R. Well, you might have some questions related to this formula. Like, why is there a negative? Isn't gravitational potential energy supposed to be positive? Because, well, let me explain this. This gravitational constant is always positive, masses are always positive, and distance is always positive. So if you multiply a bunch of positive numbers together, and then multiply by a negative 1 at the end, then your gravitational potential energy is always negative when you're talking about the grand scheme of things. Well, why is this? Well, I'll show you the integral first. Well, the integral of force with respect to displacement is equal to energy. So if we take the integral of this force formula, if we take the integral of the universal law of gravitation, so G m1 m2 and actually G m1 m2 times the distance to the power of negative 2, correct? And we take this integral with respect to, actually let's use R. We take this integral with respect to R. R is just distance in this case, because I didn't want to use d here. If we take this integral, then you get the formula for energy, which is gravitational potential energy. So if you take the integral of this, you should get negative G m1 m2 over R. So that's how you derive that formula. It's just a quick, simple integral. And you're wondering where the negative comes from. Well, when you pick a y equals 0 point, when you pick a point of 0, so a point of 0 potential energy, in your problems, you're picking it at maybe the bottom of a hill, right? Well, in gravity, technically, unless you reach out to infinity, you're still going to experience some gravitational force. So if this is maybe a trillion miles away, like 10 to the power of 9 trillion miles away, or kilometers technically, trillion meters away, well, even though if it's a trillion, you're still going to experience some force of gravity. It's going to be super, super small, but you're still going to experience some force of gravity. But how do you completely escape the force of gravity? Well, you need to travel infinitely away. And once you travel infinitely away, there should be zero gravitational potential energy because you're not experiencing any gravity. So once this is infinity, that is the only time when this problem, it's the only time when your energy, gravitational potential energies will be equal to zero. Only time. So the reason why it's negative is because we treat infinity as the 0 point. The point where you are or have zero gravitational potential energy. But negative is just an easy number as well to use for formulas and problems that you will be doing later on in your lessons of this topic. Okay, the next formula is negative gm big M over 2r. Well, what does this calculate? Well, now we're on to orbits. So all of this is related to energy, acceleration, escape velocity. Now we're on to orbits. This calculates the energy of your circular orbit. So this is a circular orbit. So if you have a sun, the circular orbit would just be exactly like a circle. Now in real life, there's no such thing as exact circles. You can approximate circular orbits. Okay, well, how about elliptical orbits? So let's draw the formula. Let's write the formula for an elliptical orbit. It's gravity times mass, the mass of the planet, times the mass of the object orbiting, over 2 times a. Okay, well, what is a? Ellip. Well, let's draw out an elliptical orbit for you. So we have a sun, planet, doesn't matter. We have a kind of elliptical orbit here. Let's mark out the components of this orbit. Well, there's a center of an elliptical orbit represented by this dot. And A is just the distance from the center to the furthest point of this orbit. So this is A right here. And A is what you'll be using for a lot of equations in your elliptical orbits, especially even the period or the time it takes to fully orbit something. Okay, well, what is C? Well, if you treat the sun like a focal point, then if you mirror this sun around the center, you're going to get something that's around here, the second focal point. And if you measure the distance between the center and a focal point, it's called C. This is called C. And you're going to be using this for formulas like eccentricity. But eccentricity is very easy to calculate, and I'll have a whole video on that. It's going to be like 2 minutes long probably. It's a very short explanation. Okay, well, how about this? Well, sometimes you can measure the distance. Sometimes people use R of P to measure the distance between your large object and the end of the orbit. So this is the closest point. R of P is the closest distance from the orbiting planet. Let's draw the orbiting planet here. R of P is the closest distance from the orbiting planet and your quote-unquote sun. And R of A will be the furthest distance. So this is if the planet was super, super far away. And you might see these variables once in a while in some of your equations or some of the problems people mention. Well, now we basically gone down to the very last few formulas. And it's to calculate the period of your orbit. So t of a circular orbit, or the time it takes to fully orbit a circular orbit, is 2 pi. Oh, I wrote a 2 pi times the distance cubed over gm. So the distance cubed is in a circular orbit is just the radius of the orbit. And g is the gravitational constant, and m is the mass of the planet. Okay, how about for elliptical orbits? Well, for elliptical orbits, quite literally it looks the exact same, except you use a instead. So a cubed over gm, and the variables all mean the same thing. So you're going to notice that most of the time you're just going to replace your distance with a. Maybe I should stay consistent with d, but d and r are the same thing. You know what? I don't even know. Why did I write r and d? You know, I'll fix all that. I'll write d here. D here. Okay. And big R stands for radius of the planet. Oh, bro, why did I do that? Like, that's just making it confusing for you guys. They're the same exact thing. I don't know why I represented them with D and R. But hopefully that didn't cause too much confusion. But if you watch to this point in the video, then I already explained it. Why I wrote D and R, I guess. But these are the formulas that you can use for the universal. You can derive from the universal law of gravitation and I explained elliptical orbits and the variables associated to it using A, C, RP, and RA. Now you're gonna see some problems where you're gonna get RP. Let me give you a tip, and you're gonna get RA. So you're gonna get RP, a value for RP and RA. Let's say RP was, I don't know, imaginary 2 meters, and RA was an imaginary 5 meters. It's going to ask you to calculate A, but all you have to do is add these two distances, RP and RA, to get 7 meters, and then divide it by 2 to get A. Since A is just, I guess, the distance from the center to the end, then you can just add these two distances and divide them by 2, and you can get their average distance from RP and RA to get A. So that's just a little tip for you if you've watched this far into the video. But as always, if you have any questions, put it down in the comment section. And if what I said today helped, or if maybe it wasn't too confusing with the RD, consider subscribing. I would greatly appreciate it. Thanks for watching.